Welcome to this brief presentation concerning contributing factors of measurement system error. My name is Bill Martin, President of Martin Business Consulting Incorporated, and this presentation of approximately 15 to 17 minutes will walk us through a couple of the contributing factors to measurement system error. Why do measurement systems commit errors we want to look at, and why isn't a calibrated gauge 100% accurate? And considering then what are the sources or causes of measurement error. In this brief presentation we're going to focus on equipment and operator and some within part variation. There are also contributing factors that have to do with environment, the measurement itself, and the procedures. Equipment. The equipment, that is the gauge, has design limitations. The gauge has display limitations. For digital gauges, the number of digits displayed is a limitation. The measurement increment of those displays is a limitation, and these are set by the design of the gauge. Gauges also have interpretation limits, especially dial readout, micrometer, any linear scale is subject to interpretation limitations. That is, the operator might attempt to make a determination of what is a value between markings on a scale. Let's take a look at a digital gauge that has a design limitation of the units of measure that it displays. In our example, our gauge is going to display to 1/1000th. So it has the capability of displaying 0.995, 0.996, 0.997, etc. When a part's actual size is different from the gauge's display capability, the gauge reports the closest available value. For the two parts indicated by the green and the red X, both of which are actually a different size, and neither one is exactly 0.998 units. But the gauge will report both of these as being 0.998. This is a design limitation of the gauge. When the actual size is directly between two values, the gauge will report either of the two available values. In this case, the part indicated by the blue X, the gauge will report either 0.999 or 1.000. If the part were measured multiple times, the gauge might well alternate between these two values. This means a window of error exists between each available display value, as indicated by the black bars on each side of the blue X. The less repeatable the gauge, the larger the window of error would be, an undesirable condition. If, however, as indicated by the graph above, the lower spec limit and the upper spec limit are 0.995 and 1.005 respectively, a part that falls between 999 and 1.0 would be of no consequence, so whichever way it measured would still be a good part. The problem exists, as indicated here by the black X in the red area on the left. A condition that is obviously out of specification. So since this part falls directly between the 0.994 out of spec and 0.995 in spec, if this part were measured multiple times, it might give different readings. Since this part falls again directly in that window of error that exists when a part falls between two values. A common practice in many organizations, if a part measures 1 unit out of spec, in this case 0.994, operators will often measure that part again. If they happen to get a 0.995, they may well pass that as a good part. The assumption being it read 0.995, therefore it must just be barely out of specification. In reality, it's a half of measurement unit out of specification, a significant amount in this case. Operators follow procedures to obtain measurements. Fixture gauging, part cleaning, location of measurements are all important, and the manual recording of the results of those measurements are important. The gauge design then and within part variation are important factors to consider. We want to, in this example, look at measuring the diameter of a round feature. Whether this is a hole, a shaft, a disc, it's irrelevant. In our drawing, it's been exaggerated for visual display. In reality, it would probably not be visually distinguishable that it was not round. But there are multiple ways to measure a round feature. We could touch that feature in 4 places as indicated by the red dots, such as a CMM program, or fixture gauging that has 4 transducers to touch in exact locations. From those 4 readings, we could calculate a best fit circle as indicated by the red circle and call this the diameter of that feature. We have an alternate method of touching the part in 3 places as indicated by the green dots. With these places, such as CMM program or fixture gauging that has 3 transducers, we could calculate a circle from those 3 points. We also have the option of touching in 2 points as indicated by the blue dots. Again, a CMM program, a micrometer, any type of linear gauging that would touch 2 places on a round feature, and we could call that measurement the diameter. As you can see, all 3 techniques give different answers. The real problem here lies with supplier-customer relationship. If the supplier uses one technique, perhaps the 4 points, and the customer uses another technique, the 2 points or the 3 points, you get different answers. Therefore, each gauge is reading its feature correctly by its design, but you can easily get in-spec, out-of-spec conditions difference between the 2 gauges. Likewise, the operator and within part variation. When the operator has unclear instructions as to the location of the measurement along the length of the shaft, they could often get conflicting results. In our feature here, we see this shaft has some taper in it, as indicated by the black trapezoid. The assumption is the sides are parallel, as indicated by the blue rectangle. The feature again is exaggerated for effect on this slide presentation. The actual feature, the taper, would not be visually distinguishable from parallel. But if one operator measured at the green arrows, another operator measured at the blue arrows, they would get significantly different readings as to the diameter of this shaft. This could also be, again, customer-supplier differences in location of measurement. So clear instructions as to the location of the measurement must be taken. The analyst must also determine, what am I trying to understand? Do I want to know diameter, or do I want to know about the existence of taper? If I want to know about the existence of taper, I must measure in at least 2 places and look at the difference in those 2 readings to understand whether or not taper is indeed present in this part. Additional causes of measurement system variation or error. The environmental conditions, distractions in the workplace, other operators, other activities, workload, cycle time, all of these things can be distractions to the measurement activity. Vibration in some manufacturing processes and with some types of gauging can cause a significant error to occur. Lighting in the inspection area. whether it's the ability to read the gauge or the ability to see the proper places on the part to locate the gauge. Housekeeping can be a contributing factor in the work area. The equipment cleanliness, i.e. the gauge. Part contamination. How do I clean the part, or do I clean the part prior to measurement? Morale of the workforce. How well motivated are they to get accurate information and to follow procedures correctly? Leadership, involvement, and dedication to the process. How motivated is leadership to ensure that the workforce follows proper measurement procedure and instructions? Measurement studies are done on many types of sources of variation. Repeatability and reproducibility, commonly called gauge R&R, are the most common, and these are often reported to the customers. Other studies include bias, or how close is the gauge to true value, linearity, which is bias over the operating range of the gauge, and stability is the stability of the gauge over time, or how often does it need to be calibrated. Measurement procedures and instructions can also help with measurement error. Well-defined instructions with no assumptions are important. We must not assume that operators know where on the part to take the measurement. We must not assume they know how to clean the part or how to zero the gauge. These must all be defined in the instructions, and the training must be adequate and it must be enforced over time, both for new operators and seasoned operators. Apathy cannot be allowed to grow in the workplace. There must be a leadership response and a motivation for employees to follow procedures correctly. Here we want to look at a value that is calculated when gauge studies are conducted. When a gauge R&R study is conducted, we report a percentage to the customer typically. But in getting that percentage, we calculate an R&R value as indicated by the red oval. The R&R value times 5.15 equals approximately 99% of the gauge error. Multiplied by 6, it covers approximately 99.7% of the gauge error. This can be utilized in understanding measurement uncertainty and a phenomenon known as the measurement uncertainty window. A given part measurement results in display by the gauge as 0.997. The only assumption that can be made by the analyst is that the part is exactly 0.997. But given that the gauge has some amount of error, what is the true value of this part? The gauge R&R value equals one standard deviation of this measurement error. So the measured value, in this case 0.997, plus and minus 2 standard deviations, gives us an approximately 95% confidence of the measurement uncertainty window as indicated by the green bars. So the true value falls somewhere within this window, 95% of the time. This becomes significant if the part measures at the specification limit. In this example, 0.995. Or it could be 1.000. In this case, we know we have a 50-50 chance that the part is out of specification. Corrective action to measurement errors. Study the measurement system analysis data. Plan what you're going to do next. What information do I need to take for the next step? Make and follow a plan to correct the excessive measurement error of this gauge. Verify all test results by repeating the tests, and then implement the corrective actions that are approved and enforce the implementation. Thank you. It's my sincere desire that everyone benefits from this brief presentation. If you have questions, contact Bill Martin, President of Martin Business Consulting Incorporated. Email me at bmartin@mbcincorp.com or call 931-637-1446. Thank you for your time and attention.